Hello everyone, welcome back to my YouTube channel. So now I am going to solve question number 3130. Find all possible stable binary arrays part 2. So yesterday we have solved part 1 of this problem. That is nothing but problem number 3129. Find all possible stable binary arrays part 1. So in this problem, if you see this, right, so you will find the same problem statement. Everything is same. So here this is part 1, so everything is same, and I explained everything yesterday as well. And if you see this part 2 today's problem, this problem, so here also everything is same. Only difference is in the constant size. So this time constant size, if you see 0 1 limit value is from 1 to 1000, but if you see yesterday's problem, so the values of this 0 1 limit, it's from 1 to 200 only. And if I just give a quick recap of this, right? So if you want, you can watch this part 1 also before this part 2, because many things are going to be same in this part 2. I'm only going to derive the code that I have written in this part 1, and I will just little bit optimize that code, and that same code I will implement in the part 2 to this problem. Same code as part 1. So here if you see in part 1, just I will go over the problem statement again. So you are given three positive integers 0 1 limit, and a binary array is called stable if the number of occurrences of 0 in array is exactly 0, number of occurrences of 1 in array is exactly 1, and each subarray of array with the size greater than limit must contain both 0 and 1. So here if you see 0 1 and limit is given to you, right? So whatever the array that we need to form, in that array we should have only 0 number of zeros, that is 1, and 1 number of 1. This is given to us. So here in this array, this is what we can form array like this 0 1, or we can form array like this. And limit 2 means, what is the meaning of this limit 2? This limit 2, here if you see this, each subarray, I'm talking about subarray of array with the size greater than limit must contain both 0 and 1. Each subarray of array with the size greater than limit must contain both 0 and 1. So here I gave you this example yesterday, that let's suppose you have some array like this, and let's say your limit value is equal to 2. Now pick any subarray of size greater than limit. So greater than limit means you can pick this subarray of size 3, maybe of size 4, of size 5. You can pick any subarray, right? So in this subarray you must find both 0 and 1. If it is not there, like both 0 and 1 are not there in that particular subarray of size greater than limit, then that simply means that particular array is not stable. So here if you see this, in this particular example, in this array limit is 2, so greater than limit we have to pick that's what size of subarray. So let's say I pick this. So in this, if you see, you don't have all you don't have see 1 anywhere here in this subarray, so it is not stable. So each subarray of array with the size greater than limit must contain both 0 and 1. Here you are already seeing zeros. So here size is 3 that I'm taking as of now. Limit is 2, so I'm taking a subarray size of 3. And in this 3, I see all zeros. So that is why it is not stable. It should contain both 0 and 1 for an array to be stable. So now what does this simply means? This simply means that at most we have limit times consecutive zeros or ones. So I should not have more than limit consecutive zeros and 1. So here that simply means we should only see 2 consecutive zeros or 1 if my limit is 2. If I'm seeing 3 consecutive 2s or 4 consecutive zeros, or 2 consecutive 3 consecutive zeros, or 4 consecutive zeros, or 5 consecutive zeros, so simply that simply means that this array is not stable. So this is what we already discussed yesterday. So this array is not stable because here we don't see limit number of consecutive zeros only, because we are seeing more than limit number of consecutive zeros, right? So that's simply what I'm saying here. Clear? So this actually we discussed everything yesterday. So here if you see in all this example, limit is 2, So you should not see more than limit consecutive zeros or ones. So 2 is okay, so 2 times 0 or 2 times 1 is okay, but are you seeing anywhere 3 times zeros here or 3 times ones here in these all possible stable binary arrays? No. So this is what we have given right in part 1, and part 2 is also same, only constant size is this. So in part 1 actually our time complexity was this 0 into 1 into limit. This was why my time complexity in part 1. So that's it means 200 into 200 into 200, that is nothing but 2 into 2 is 4, 4 into 2 is 8, and how many zeros I'm using into 10 raised to power 1 2 3 4 5 6. So this is going to be my time complexity. Clear? So this is nothing but 8 1 2 3 4 5 6. So see 8 million operations I'm doing, right? 8 million operations I'm doing here. So that is accepted. So you will not see any time limit exceed issue. But in today's problem part 2, this value is not 200, this value is 1000. So now here, if this is 1000, so can I submit the same code again? Is it possible? So here this is nothing but 10 raised to power 9. Definitely we will get time limit exceed error. So this is not possible. So now we have to fix this issue, right? We have to optimize our code. So yesterday I have shown you the top down recursion approach, recursion tree. So like you have to use 0 or 1, right? So here if you see this example number 3, so 0 is equal to 3 times, 1 is equal to 3 times, so limit is 2, and limit is 2 means we can have, if we start from 0, so I can have 0 in the starting, or I can have two zeros at most. It should not be more than limit. If I start from 1, so at 1, 1 time 1 or 2 times 1 I can have. Now if I am using 0 here, then next time I have the option to choose just 1 time 1 or 2 times 1s, right? So this state diagram also I explained in yesterday problem. If you are using 1 here, then in the next step you can use 0 or 2 times 0. Same way, if you have 0 here, you can choose 1 or 2 times 1. Same way, here you have 1, so here you can choose 0, or you can choose 2 times 0, 0. But it is not possible, because here, if you start from here 0, then you go to this 1, then here 0. So 2 times 0. So overall 3 times 0 you have already used now. So here if you create one more 0, 0, so you are using 4 zeros, but we have in total 3 zeros only, right? So this is how we formed the tree yesterday, right? So now here if you see this, so 1 0, if you just form this array, okay, so here if you see 0 1 0 1 0 1 0 1 0 1 0 1, okay, so this is the array you are forming. Same way here 0 1, then if you follow this path 0, then here if you go 1 1 and then 0, so here 6 length, okay, length should be 6 na, 0 plus 1, 3 plus 3 6. So this is what we discussed. And here if I just show you the code for this part, okay, so first we solved this using simple recursion, right? Then we implemented memoization. So let me show you just a simple recursion, okay, what we did here. So this is the main method, right? Number of stable arrays. So in this I'm starting from I'm counting the arrays, okay. Here I'm starting from 1 0, the number of zeros given to us, and here what I'm passing, here I'm passing 0. 0 means the last placed, let's say last I placed 0 and limit value, and here last I placed 1 and then limit, okay. So last placed is this thing, right? So 0 is fixed. Now after that I am proceeding, I have these many options. If 1 I fixed, then after that I have these many options, okay. This is what I'm doing here, all right. So this is what I'm doing here. And here if you see this count arrays, this is also very simple in count arrays. So when you have to stop, so you have to stop when your number of ones left in the end, okay. Here you are forming one array, so in the end if you see number of zeros, you have already used all three, number of ones you already used all three, so then you have to stop. So this is what I am writing here. If all elements are used, we form a valid array. And then we have to calculate the number of ways. Okay, so if last placed is 1, so if last element was 1, now we have to place a block of zeros, right? So here, how many max zeros we can place after that? So that depends on the number of zeros we have in total, okay, or number of ones we have in total, and we have to compare that with limit. So this also I explained here somewhere. So if you have just one and limit is 2, so only one more one you can place in next step, even if you have a limit is to 2, right? So if you have 0, so here if limit is 2, so maybe next time 1 and 1 you can place. But if you have only one is remaining, only one time is remaining, then you definitely can't use this even if you have limit 2. So that is why here max, if we last place is 1, so next time we have to place 0, so max zeros we can place is min of this, right? And then after that I was checking, like for length is equal to 1, right? And up to max zeros we can place. So 1 0 if I add in the next state, or if 2 zeros I can add in next state, or if 3 zeros I can add in that state. So I am checking all these possibilities and I am counting the number of ways. And I definitely have to do the mode. Same way if last placed was 0, so I was doing this thing, and then we have to calculate the ways. So this code, simple recursion I was doing, but we were getting time limit exceed issue. Then after that, what I did, I moved to the second part, that is same code, but I implemented the memoization. So we know that only three things are changing here: one left, zero left, and last placed. So I created the memo of this, and here I initialize the state of memo to -1. And once I did this, then whatever the answers that we were getting, so here I was storing that in the memo, and I was doing early exit if somewhere I already calculated this value in the past. So this is what we did. So this is nothing but your recursion approach, top down approach. Then we change the code of this top down to bottom up in yesterday's problem, right? So here if you see this, so same way, right, we created one dp, 1 plus 1 0 plus 1, this is what we did, right? And then base case, if you have no 0 left, no 1 left, and last state was 0, so only one way is possible. Same before this one also, one way is possible. If last state is just 1, last place is just 1, and you have nothing else, right? So you have to take 1, and then you were running this loop, right? And this is same code, like I converted this code, okay? So here if you see this, so here I show you how I changed this code step by step to this bottom up dp approach. So using that, we change this code, same thing that I write there, same thing I was writing in this part, okay, in the recursion measure, same thing I'm writing here. So now I'm going to little bit optimize it now, right? Because if I just place copy this code and place it here, and I run it in part 2, so let's see what will happen. All test cases has been passed here, but when I try to submit this code, see here I'm getting time limit exceed issue. 574 test cases got passed, 580 out of 582, right? So now we have to optimize it. So let's see how we are going to do that. So now let's fix and optimize our new code that we are going to write for part 2. So here if you see, we are running this loop here for this much time, for this one this much time, and again inside this also we are running this for limit. Let's say limit is minimum among this, so limit number of times. So time complexity is like this now, 1 into 0 into limit, and this was the issue in part 2, in which the constant size is large. So we have to optimize it now, this one. So here if you see, dp of ones left, zeros left, and 1, so here we are storing this ways. And how this ways we are calculating, in this ways we are calculating like this: dp of ones left, 0 left minus length, here 0. So here 0 left minus 1, then in the next case it will be 0 left minus 2, like this we are driving it further. So this we need to optimize. Okay, so let's see how we are going to optimize it. So what is a DP state meaning? DP ones left, zeros left, last place. It simply means number of ones remaining, number of zeros remaining, and last placed. So 0 is the last element in the array is 0, 1 is the last element in the array is 1. So DP of here, if I just write instead of ones left, if I just write here O Z and here 0, so that simply means number of array with O ones, Z zeros ending with 0. Same way, number of arrays with O ones, Z zeros ending with 1. Okay, so base case is like this. If we only place zeros, right? So if we only place zeros, so like this, so it is only going to be valid only if the length is less than equal to limit. So 4 zeros left. Okay, so let's say how many zeros you have left is the total number of zeros and the limit. Consecutive, you can use this much only. This we already discussed in the part 1. So here, let's say number of ones remaining is 0 only. Zeros you have left. Okay, zeros you have left from 1 to, let's say, up to the min of this, the 0 and the limit count, right? So this is what remaining, and last place is 0. Okay, last place is 0. So from this, there is only one way, right? There is only one way for all these base cases, right? Because here if you see limit, let's say 2, so if I take this, then also there is one way. If I take this, then also there is one way. So in all the cases, number of ways will be one only, right? And this will be invalid because limit is 2. Same logic I'm going to use for this one left. 1 to min of 1 comma limit, and here one's left, and here I'm saying that number of zeros, there's now no zeros left, and last place is 1. So here, even if you place only one, then also one way. Even before it, if you place two ones, then also there is one way. Okay, so all these base cases I'm setting it to 1. So this is done. Clear? Then we have to fill this DP table, right? So ones left and zeros left. So we are going to skip cases where one side is 0 because base cases already handled them. So here base cases already handling them, right? All this stuff. Now case 1, array ends with 0. So to end with 0, previous element can be 0 or 1. So I'm saying that if array is ends with 0, so here and here 1 0 I have already consumed, right? So I will say z minus 1, z minus 1, and here once is going to remain same, and this element, it may end with 0 and this may end with 1. That's the meaning of this thing. So to end with the 0, previous element can be 0 or 1, right? Because we append 0 to any valid array with in which we may have O number of ones. Okay, we didn't utilize anything yet, and z minus 1 number of zeros. So here see O and z minus 1, O and z minus 1, right? Because we append 0 to any valid array with this O number of ones and z minus 1 zeros. Okay, before this case. So this I break it down to like this. Okay, but we must enforce the limit. We can't allow more than limit consecutive of zeros. So if last is 0, then after that we have to make sure that I don't want to cross the limit number of consecutive zeros. So we must remove sequences where we already had limit zeros before, right? So that means patterns like this. Let's suppose here we have limit zeros already. So now if we add one more zero, then it is going to look like something like this. So it violates the rule. So those bad sequences are dp of 0 and here z minus 1 limit and 1. So we subtract them using this equation. So this is the equation. Now how this equation is coming up, we will see that. Okay, no worries. So here, let's suppose you get something like this. So you can further write it like this. Okay, so these two parts I'm writing it here, and I'm only subtracting this from these two if the zeros left is greater than limit. Otherwise I will get some negative index here na. So that's the purpose. So here first I calculate these two and I put this value in this. So now this complete contains both these two values, and now here from this I am going to subtract. Okay, from this one I'm going to subtract this one, right? So I will show you this in code, right? So same way here, if your array ends with 1, so if it ends with 1, so 1 count will be decremented both times and z will remain same, and here you may use 0 and may use 1. Okay, you have to calculate the result for this case now, like this. So append 1 to any array, so that simply means previous, so you will see 1 minus o minus 1 number of ones and z number of zeros. So enforce limit for ones, so remove cases where we already had a limit times of ones. Okay, so this is what we need to remove. So I'm going to remove this using this. Okay, and same type of formula that I'm going to drive here. Okay, the formula that I derived here. All right, so here if you write it in better way, you can write it like this, right? So now the array may end with either 0 or 1, right? Your array may end with either 0 or 1. So we have to calculate the result of both. Initially what is 1 and 0, and it may end with 0, 1 and 0, it may end with 1. So whatever the result with these two cases, that we need to return. Okay, so now this is a little bit optimization. Okay, so instead of this I'm just going to use that formula that I have derived, these two formulas. All right, so now let's see that how I'm going to drive those formulas. So here dp of 0 1, dp of 1 0 and 1, right? So here if you see overall we are filling these values only na. dp of 1's left 0 left 0, 1's left 0 left 1. Okay, so dp of oz1, dp of oz0, only this we need to calculate, right? And these we calculate in base, and in base we are implementing this thing. Right now I have to find a shortcut instead of here running over the loop 1 to this maximum we can place. I don't want to do that, I want to optimize it. So what I will do here, this code, in this code, so let's go here. So this case, right? So number of arrays with o number of ones, z number of zeros, and ending with 1, and no more than limit consecutive ones. So this we need to subtract, remove, right? So think about the last block of ones is like this. If the array ends with 1, then the last block of ones must be this much. Let's say it's limit number of times. It is not limit plus 1, it is only limit number of times, so it is valid because we can't exceed limit. So k is the number of trailing ones, let's say. So k value is from 1 to limit. Okay, it can be anything. So every valid array looks like this, 1k times and then prefix ending with 0. All right, some prefix ending with 0 here, right? And here we are not taking more than 1k consecutive ones. Okay, more than k, right? So example, when the limit is 3, so I can use 1 time 1, I can use 2 time ones, I can use 3 time ones, and here maybe I will use 0, and here again I can use something else in the past, right? But I'm not using consecutively 1 more than limit number of times, right? So now count each case. So if a suffix is, let's say, 1k, then the prefix must contain the prefix, okay, prefix element, it must contain zeros z, and here I have to subtract this total number of ones o minus k, right? This is what I have to subtract now, and that's it. And must end with a 0. So here see all these prefix are ending with 0 only. Clear this part? Clear this part? So the number of such arrays is nothing but, so I can say dp of here this and this, and here I have to write 0 because all this should be ended with 0, and here z will remain this, and here o minus k. Okay, I subtracted this o minus k, right? So this is what I get. Now sum all the possibilities, since k can be from 1 to limit. All right, this k can be from 1 to limit, so we have to check for all the possibilities, right? So what I will do here, in this k is from 1 to limit, I will calculate all the values, and I will pass all these values in the this dp of o z and 1. So this is what we are driving here, right? This is what we were driving here, dp of oz1. Okay, oz1, right? Clear this thing? So this equation is the real definition. So now we can't use this in the code directly, right? Because if we compute that sum every time for k is equal to 1 to limit, time complexity is going to become this too slow, right? So we have to now little bit optimize it. So how you're going to optimize it? So in this, if you calculate the sum, so let's say your k is 1 first time, so
o minus 1 z 0. Then next time let's say your k is 2, o minus 2 z and 0. Then next time like this. Okay, so now inside this let's further break it. Okay, so expand the dp of o minus 1 z1. So this I calculate. Now I have to further break it. Okay, how I'm going to calculate this formula? So very simple now. This formula is for this one. Same way, if instead of o I write dp of o minus 1 and z and 1 here. So in same way here also k is equal to 1 to limit. Here also dp of o minus 1 minus k and here z and 0, like this. I just modify this o to o minus 1. That's what I did here. All right, now again, now if you solve this part, okay, but before that, in this equation whatever you have here, right, so here if you see you have something like this, dp of o minus 1, o minus 1 and z of 1. This is what you have now. So I am saying add this dp of o minus 1 z 0 both sides. So here dp of o minus 1 z 0 plus dp of o minus 1 z 1, right, this you are adding, and here same thing, in this side also you are adding the same thing. So it will not create any impact, right, both will cancel out each other. So but I am adding it right now, and here k is equal to 1 to limit and this, right. So now what will happen? What is the purpose of this? Purpose of this is that k is, I am starting from 1, so I am planning to start my k from 0, right. So here if my k is 0, so that simply means this. Okay, 0 minus 1 z 0, that simply means this case. So here I can completely, I can write this like this now, k is equal to 0 to this and then limit, right. So here what is the meaning of this one? Meaning of this one is this, all right, dp of 0 minus 1 z 0, right. Okay, so now from this step we get this, okay, and from this step we get this. So from step 3 we get all these values. Same way from the previous step, what we get something like this. Okay, that is nothing but dp of 0 minus 1 z and 1. This is nothing but equal to this, all this. So dp of 0 minus 1 z 0, then plus dp of o minus 2 z 0 plus dp of o minus 3 z 0 up to here dp of o minus 1 o minus 1 minus limit z and 0. Same way before this, one term before this, that is going to be dp of o minus limit only and z comma 0 in this and in this, right. So here this term is here, this term is here, everything is here, right, up to this. So up to this everything is in this, right. Clear this part? So only one extra term is this. Our current sum has one extra term, right. So here whatever I am calculating here, I can say this is nothing but dp of this o z and 1, and in this we have one more extra term. Actually overall we are calculating a result of this now, we are calculating the result of this here, this part. Okay, this part, not this part. This is nothing but the extra term is o minus 1 minus limit and z and 0. So this is nothing but the right hand side part now. This is nothing but right hand side part. So in both the sides what we did, we added this now, dp of o minus 1 z 0. So now this is your LHS part and this is your RHS part. So RHS part I simply grab it like this. So now you can further optimize it. This is what we need actually in the end. So dp of o z and 1 is nothing but in the left hand side these two values. So normally what we do, o minus 1 z and 0, right. So in the past if I have already used 1, so 1 is already consumed, o minus 1 o minus 1, and here z and here z, and here you may have 0, you may have 1. Okay, so that's what now here this plus dp of o minus 1 is already happened, z and there may be 1, and from this you have to subtract this extra term. This extra term goes to this side now. this LHS side. So minus of dp of o minus 1 minus limit, and here z and 0. So this is the formula that is written over here, and this same formula, if you see here, I am going to use in the code. Okay, so dp of ones left, zeros left and 1 is nothing but it is equal to 1 left minus 1 0 left 0. So 1 left minus 1 0 left 0. Okay, plus of dp of 1 left minus 1 0 left 1, 1 left minus 1 0 and 1. All right, this is what I'm using. Right, this complete I am storing, this complete thing I am storing in this, and then from this again I am subtracting this part. So here if you see, if only I have to make sure that one's left value should be greater than limit. So once left is greater than this, then again I am operating this same thing with, I'm again writing the same thing, right, this same thing, and from this now I'm subtracting this 1 left minus 1 limit and 0 left, 1 left minus 1 minus limit and then z and 0. Okay, and we have to take mode. So this is for and with 1. Same way you have to derive this same formula for this one, so you can apply the same thing. And here see, in yesterday's code again I was running these loops only, right, and the base cases I am writing here. So this is actually your code for this second part, right? So let me just submit it one time. All right, and then I will go over the code. So see, our solution is empty, right? So if you compare this with this part 1, right, there are minimal number of changes, not much. Okay, so here this is, here again I was using this loop, right, last time, 0 left, right? So again same thing I'm doing here, if you notice, right? And base case I already told you that 0 left is less than equal to math.min, and this is how we have to write the base case this time. Okay, and inside this if anyone is 0, so we already entered this in the base cases, so we are skipping it. And here I show you how we writing this, okay, using the formula, how we drive that formula. And in the end, initially we have this 1 0 and 0 can, may our end array may end with 0 or our array may end with 1. So we have to check, calculate the both the result, and then we have to take the mode. So this is what we have to do, right? So just go over this code and go over these things, right, and you will get very much better idea about this, how we are doing this. All right, so I hope that you guys are clear with this problem, and if you guys still have any doubts, then please feel free to ask in the comment section. Till then, keep coding and keep practicing. Meet you guys next video. Thank you, bye bye.